So, what is big O notation? In plain English, it's a fancy way to measure just how gloriously your algorithm is going to fail as your input size grows. Sounds uplifting, right? Let me explain. In maths, you have these little magic boxes called functions. They take some input and give some output. Each input has exactly one output. Except when they don't. Freaking square roots. Well, we can ignore those. Let's take a deeper look at this function. When we pass in a value, we substitute it for x. After putting this into our calculator, we get an output. Graphs are useful. They allow us to represent math functions in an elegant and visual way. Each point on a graph can be represented by a pair of values, one representing the x-coordinate and one representing the y. This is pretty intuitive if you've ever played Minecraft and hit F3. Typically, functions represent graphs. Here we have one with an x-axis and a y-axis. Since our input variable was x, our output in this case will be y. Let's start by graphing this function by putting some numbers in for different x values. This is the final graph. Okay, why does this matter? I don't care about x's, and I don't care about y's. We're trying to write some computer program. We want it to be efficient. That could mean minimizing how much time or even space it takes. What increases those things? Let's say we have some function which prints numbers from 0 to n, waiting 1 second between each print. As n increases, the function will have to wait n seconds. If we want to print, say, 10 numbers, it will take 10 seconds. We can graph this relationship. Now, x means the size of our input. So basically, what value n is. And as n increases, the time taken for our program increases. So the y-axis represents time. This means we can represent any computer program performance as a mathematical function. Talking about big O notation, we refer to it as the general function. It's big, and it's pretty precise. One thing you'll notice is that when we go further out on the x-axis, or as the calc judges would say, as x approaches infinity, that the first order term dominates the value. The constants and lower order term begin to matter less and less, becoming tiny blips. What if we completely ignore them? This gives us a reference function. Sure, way less accurate for smaller values, but it's good enough, and it simplifies comparing algorithms, especially on large scales. Now that we have our reference function, we can just put no and wrap it in brackets. This is a way of saying, hey, this is the worst case scenario of our program. It can't get worse than that, in terms of runtime or space complexity. That's literally it. You now know what big O is, and you understand how we get to it, and the intuition behind it. There are some neat patterns we can use to predict what the big O of our code will be. O of 1, for example, is constant time. It happens when an algorithm or action is independent of the input size. Then we have O log n, known as logarithmic time. We get this by solving a big problem and then transforming it into a series of smaller problems by cutting the problem size by some constant fraction. When you divide a problem by n, it becomes log to the base n, but we ignore bases when getting the reference function. Then we have O of n, known as linear time. We get this when we do a bit of processing on each input. Then we have O n log of n, which is linear arithmetic time, which we get by solving a problem by breaking it up into smaller subproblems and then solving them independently, then combining them. Then we have n to the power of x, known as polynomial time. We get this by processing data in x groups, so pairs or triples. An example would be having nested loops. Then we have exponential time, or 2 to the power of n. We usually get this through brute force solutions. They're pain, they're hell, they're chaos, avoid them like the plague. Big O notation lets us compare algorithms in a meaningful way, without sweating the small stuff like constants or implementation quirks. It tells us whether our algorithm scales gracefully or falls apart under pressure. Whether you're working with prime numbers, sorting, or any other problem, Big O is your go-to tool for thinking about performance, without needing to dive into the nitty-gritty every time. Thanks for watching. This has been Mo.